Remember that we talked previously about the relationship between the length of a vector and that vector dotted with itself. Well, directly from that definition or that relationship comes the Cauchy Schwarz inequality. And this inequality tells us that if we have two different vectors, we'll call them A and B. So if we have the vector A and we dot it with the vector B and we take the absolute value of that dot product, that's always going to be less than or equal to the product of the lengths of the vectors. So we have the length of the vector A multiplied by the length of the vector B. So when we multiply the lengths together, that value is always going to be greater than or equal to the absolute value of the dot product of those same two vectors. Now you'll notice here that we're saying that the dot product value, the absolute value of the dot product, is less than or equal to, which means that, of course, sometimes the absolute value of the dot product is going to be less than the product of the lengths, and sometimes it's going to be equal to the product of the lengths. Well, interestingly enough, these two values, the left and right-hand side, will only be equal to each other when A and B are scalar multiples of each other. In other words, where we can say the vector A is equal to some scalar times the vector B, or equivalently, we could write this as the vector B is some scalar times the vector A. These two equations are really saying the same thing. It's just that if in this first equation, let's say C is equal to 2, that means in the second equation that C is going to be equal to 1/2. So you get a different value for C, but the point is that the vectors A and B can be related by some scalar multiple. We just multiply a scalar by one vector and we get the other vector. In that case, the vectors A and B are parallel to one another, or we say that they are collinear. Either way, the vectors A and B are linearly dependent when that's the case. And that is the most interesting property for us right now of the Cauchy Schwarz inequality. It gives us a test for linear independence. It tells us that if we find these two values on either side of the inequality and they turn out to be equal to one another, then we know that the vectors are linearly dependent. If the values are unequal, in other words, we say that the left-hand side is less than the right-hand side, then we know that the vectors A and B are linearly independent. So let's take an example where we know that the vectors are already linearly independent. Let's use the standard basis vectors I and j, where I is 1, 0, and j is 0, 1. We already know that these vectors have length 1, but if we didn't know the length, remember that we find it this way. We say the length of the vector I is equal to, we square both components, so we say 1 squared and 0 squared. We add them, and then we take the square root of that value. So the length of I is going to be the square root of 1 plus 0, or just the square root of 1, and we know that that's equal to 1. And the same will be the case for j. Its length is also 1. And then if we take the dot product to get this left-hand side here, the dot product of I and j, we'll say that I dotted with j is going to be equal to, we multiply the first components together, so we get 1 times 0 plus the product of the second components, 0 and 1. So 0 times 1, and of course we get 0 plus 0, or 0. We need the absolute value of that dot product, but of course the absolute value of 0 is just 0. So if we put those into our inequality, we say 0 less than or equal to, because this is the left-hand side here of the inequality, and then the right-hand side, we just have 1 times 1, because the length of the two vectors are both 1. And we get 0 on the left-hand side, we get 1 on the right-hand side, and we can say that 0 is less than 1. Because we get that less than relationship, that tells us that the vectors are linearly independent, which of course we already knew since these are the standard basis vectors, but we can see that it works there. What if we take an example of linearly dependent vectors? Let's make up a couple vectors. Let's say that we have the vector A, which is equal to, let's say, 2, 1, and then we multiply that by, let's say, -3 to get the vector B. So if we multiply 2 by -3, we get -6. If we multiply 1 by -3, we get -3. So because we've multiplied A by a scalar multiple of -3, we already know that A and B are linearly dependent. But let's make sure that the Cauchy Schwarz inequality shows us that they are in fact linearly dependent. So again, we'll start by finding the length of each vector. So the length of the vector A will be equal to, we'll take 2 squared, 1 squared, we'll add those together, and then take the square root. That's going to be equal to the square root of 4 plus 1, or the square root of 5. If we take the length of B, so the length of the vector B, we'll square both components. So we'll say -6 squared plus -3 squared, and then take the square root of that value. We'll get the square root of 36 plus 9, or the square root of 45. Remember that 45 is the same as 9 times 5. So this is really the square root of 9 times the square root of 5, and the square root of 9 is 3. So this is equal to 3 times the square root of 5. And then we need the absolute value of the dot product of the two vectors. So the absolute value of the dot product of A and B will be equal to, we'll say the absolute value, and then the dot product will be the product of the first components 2 and -6, so 2 and -6. And then we add to that the product of the second components 1 and -3. So 1 and -3. And that's going to be equal to the absolute value of -12 minus 3, or the absolute value of -15, which is 15. Now, if we put these together in an inequality, we take this value 15 for the left-hand side. So let's go ahead and put that over here. 15 less than or equal to. And then the right-hand side is going to be the product of the length of A and the length of B. So we'll say square root 5 multiplied by 3 times square root 5. We have 15. And then on the right-hand side here, square root 5 times square root 5 is 5. So we get 3 times 5, or 15 on both sides. And so what we can see is that these values are equal to one another. So because we get that they're equal, that tells us by the Cauchy Schwarz inequality that these two vectors A and B are linearly dependent, which we already knew because, of course, we said that -3 times the vector A was equal to the vector B. We were able to write these as scalar multiples of each other, just like we showed here, where we said if we multiply some scalar C by the vector A, we get the vector B. So because they're scalar multiples of one another, they are linearly dependent, and we were able to show that with the Cauchy Schwarz inequality.